All right, back with the second half of chapter 4. In the previous movie, we had talked about, or I had talked about, the different variations on carbon skeletons, these hydrocarbons that we had talked about, and the fact that carbon as a molecule oftentimes lends itself to being able to have these variations. Okay, now we're going to talk about even more subtle variations within similar chemical formulas. Okay. We're going to talk about isomers, and there's some really interesting talking points about isomers. An isomer is a molecule that has the same molecular formula as some other molecule, but it has a different structure. And one of the things that's important to understand about this, and maybe I didn't point that out well enough, is the fact that isomers, although they have the same chemical formula, same molecular formula, they have different structures, as I mentioned, but they will also have subtly different properties. Okay, so if we look at these sets of molecules, you saw the other one pop up already. I want you to just kind of briefly go through them. Maybe you pause the video and see if you can't decide which of these are isomers and which of these aren't. Okay, so you're going to look at each example and say to yourself, okay, are these two, okay, this molecule here and this molecule here, are they isomers of one another? Meaning, do they have, number one, the same chemical formula, and do they have different structures? How do we tell if they have the same chemical formula? Well, easy. Okay, we can count the number of atoms of each type in each molecule, and that's the easiest way. Okay. When we look at this one, obviously there's a different number of carbons, right? So that's automatically not going to be an isomer because it doesn't have the same molecular formula. If we look at the second one, we can look at that one and say, okay, they look different. Okay, so they do qualify under the different structures. Let's see if they have the same molecular formula, same chemical formula there. Okay, we've got 4 C's. I count 4 C's, 1, 2, 3. And then we got 10 hydrogens, and do the same thing to the other one, to isobutane. Okay. Yeah, it's got the exact same. It's C4H10 on both of them. So yes, these two are going to be isomers. Okay. Now you'll notice that the difference is it's as if they've taken this right here. It's like they took this, what we call a methyl group. Okay, a CH3 is called a methyl group. Lopped it off, just chopped it off, and placed it right here in the middle. Okay, basically just took this H and this big chunky CH3 group and switched them. Okay, and so it doesn't seem like a lot, and it's got the same chemical formula, but these two things are different. Okay, they will have different sets of properties. Okay, again, you can look up what those properties are if you are that interested in it. This one we've kind of talked about already, 1-butene versus 2-butene. So I think I might have even mentioned that those two in those drawings I did were in fact isomers. Okay, again, we look at them. Okay, say, okay, they've got C4H8. Okay, C4H8 for both of them, great. So what is different in this particular structure? Well, it's the placement of the double bonds. We see the double bond here is off the first carbon, and the double bond here is off the second carbon. Okay, just that subtle difference, even though they've got the same chemical structure, is enough to give them distinct sets of properties. All right, let's look at this other one here. I think this one ought to be pretty easy, whether it's yes, an isomer, or no, not an isomer. We look at the number of C's versus versus C's. Those are the same. We look at the number of H's. Okay, that's what's wrong. There's a billion H's on one of them and only 6 on the other one. Okay, so that one would not be classified as an isomer. Now, when we get into isomers, we have to discuss the different varieties. There are different types of isomers, guys. And part of what we're going to talk about in this portion of the video are these different types of isomers. Okay, so we've got something known as geometric isomers. They vary in spatial arrangement, and these will make more sense when you actually see them and are shown models of them and things like that. We've got structural isomers. The atoms vary in covalent arrangement. All of the isomers that we saw on the previous slide were examples of structural isomers. Okay, double bonds were put in different spots, or maybe a functional group was moved from one place to another, or whatever. Okay, stereoisomers, also known as enantiomers, that's a tricky one to say, vary in spatial arrangement around an asymmetric carbon. Again, those definitions are kind of official. They use big language. But when you start to see pictures of these things and models of these things, they're going to become a little bit more easy. Okay? So the structural isomers, we've already seen plenty of examples of these things here. The one that you see in front of you is the example that was given 2 slides ago in the little quiz session, if you would call it that. We've got butane. You know that one well by now. You've seen it 3-4 times already today, or in this chapter. And the one we see over here is called methylpropane. Okay, and basically, like I said before, what you see is basically this. Let me see if this stupid pen works. It wasn't working the other day. Blue. It's as if we took this. That sucks. We took this hydrogen here, and we switched it with this, what is called a methyl group. That thing I was trying to do that. That is called a methyl group. If we took those things and switched them, now we have this thing called methylpropane. Okay, where we took that methyl group and we put it right in the middle of the existing, what is now a propane molecule. Okay, so that's the other thing about organic chemistry. They got a half a dozen different ways of naming different things. Okay, what you saw on the previous slide, I might go click back. Let me get rid of the terrible pen that doesn't work. You saw that same thing called isobutane, but over here they call it methylpropane. Okay, different ways of naming things. Don't worry about it. You don't have to know that. All right, the ones that are a little bit more difficult to understand and conceptualize are geometric isomers and also the enantiomers, the stereoisomers. So let's get geometric isomers out of the way. They have the same covalent partnership but differ in the spatial arrangement. Now, when you look for geometric isomers, if you ever have to identify geometric isomer, you are going to look for a double bond in the molecule. And that's exactly what we see here in this example. We see a double bond in this example. We see the double bond right here in between the 2 carbons and the double bond here between the 2 carbons. Now the difference comes, and let's qualify it and say these both have the same chemical formula. There are 2 C's, 2 H's, and 2 chlorines. This is something known as 1,2-dichloroethene. Okay? But they are different from one another. Okay, both of them are called 1,2-dichloroethene, but they are different from one another based on where the chlorine molecules happen to be. That is what they're talking about by the having the same covalent partnership but different spatial arrangements. These chlorines are arranged differently in space. Okay, this one right here, which is called the trans isomer, is it has the chlorines across the double bond from one another. That word root trans, if you are doing your word roots or have gotten this far or have seen that one yet, I don't know if you would have seen it yet or not, will realize that term trans means across, okay, when used here. If you've ever heard of a transcontinental flight, that means you are taking a flight across the continent, okay? So in this case, the term trans isomer, or we could call this one trans 1,2-dichloroethene. That's how you would say it in college when you get to learn this. That indicates to you that the chlorine molecules are located across the double bond from one another, okay, or far apart from one another, okay? Now, if we look at this other example, the cis isomer, this one would be called cis 1,2-dichloroethene. Again, something you don't have to memorize or even know. But this cis isomer, the term cis means adjacent to or next to or near. Okay, and if we look at the arrangement of these chlorines to one another, they're pretty close. They're near each other now. Here they were far apart. They were across that double bond, very far from one another. Here they're close to each other. Okay, the way I always remember the difference between cis and trans isomers is if we look at these cis ones. How many of you guys have sisters that you're close to? Generally, this applies to girls who have sisters, but that's not always the case. I know plenty of guys who are really close with their sisters. But classically, my mom had all sisters, and she's really, really close to them. They go to wineries, and they go hang out with each other. They go to Europe together, and blah, blah, blah. And so they're very close together. They're very close-knit family. They love each other very much, right? And so this cis isomer sounds like sisters, right? And sisters are close. Get it? I don't know if it works or not, but it works for me. So these two functional groups, the chlorines, are located near each other or close to each other, and so you could call this one the cis isomer. All right. This one up here, I always remember the transcontinental flight, a flight across the nation or across the continent, and so the chlorines are located across from one another. Okay. Now, the reason that this has to, I'm gonna click out and go to the document cam here real quick. Now, the reason that we have to have this double bond is because of that idea of 3 dimensions. So this is a model of what I've just made. Okay, this is a model of what I just made. And let's get rid of this double bond first here. And disregard all of the improper bonding. Okay, remember how I said things, when you talk about organic chemistry, things move in 3 dimensions, and oftentimes they move in 3 dimensions like you wouldn't normally think of, right? But when a couple of atoms like these 2 carbons, when they are connected by a single bond, there is actually rotation around this single bond. So this molecule right here is the same as this molecule here. There is no trans isomer here. There is no cis isomer here. Because 1 second it could look like this, and then the next second it could rotate down here and look like this, and then the next second it could rotate back here. It's the same thing, okay? There is rotation around that single bond. Now, the reason that that double bond all of a sudden makes this new type of geometric isomer possible is because when you make that double bond, it all of a sudden locks those 2 carbons in place. There is no rotation. I'm trying to rotate that thing. I'm going to break it if I do. I'm trying to rotate it, and it just won't rotate. So when you put a double bond here, it sticks it into this case, which is the, take a guess, pause it and take a guess, the cis isomer. And if you happen to have something where the molecule was put together like this, you would have the trans conformation because there is no rotation around that double bond. That's why when you talk about geometric isomers, it is essential that you have this double bond intact there. Okay? So keep that in mind. Geometric isomers always have to have that double bond. Okay. Toy time is over for a second. We're going to get back with the toys in the next slide, though, so that's going to be fun. All right. The next one we'd talk about, the next type of isomers we should talk about are called enantiomers. That's a fun one to say. I like the term stereoisomers a little bit better. But enantiomers are molecules that are mirror images of one another. Okay? They usually involve an asymmetric carbon. So I'm going to go back here. I should have just left it open. Get rid of that guy. I'm going to put these guys right here. And you look at those and you tell me, okay, I see those settling right in front of me. You're going to say, I'm going to ask you, are those the same or not? Are those the same or not? And you'll look at them and be like, oh yeah, they got a carbon in the middle. There's a red thing, a blue thing, a green thing, and a silver thing. Yep, those are the same. Those are the exact same. And if we were in class, I would attempt to have you prove your answer. I'd say, okay, you prove to me that these are the same. And so I'd throw them to you, and you'd kind of look at them like, how am I supposed to prove that they're the same? Well, one way that you can prove that these are the same is you can try to lay them on top of each other. And if they match up color for color, then they're the same. Okay? They look at first glance as if they are the same. They got the same colors, and they all kind of look like the atoms are put together on that central carbon the same. So let's try matching all the colors up together. Let's try matching the red and the green first. Okay. Red and green, we match them up. Okay, red and green are matched up. But are the blue and the silver matched up? No, they're off. Okay, looks like blue is matched with silver. That's not right. We need the blue to match with blue and silver to match with silver. All right, let's try silver and blue. Let's try getting the silver and blue matched up, and hopefully green and red will take care of themselves. All right, silver and blue. All right, they're matched up. Looks good. Let's look at the greens and the reds. Are they matched up? Nope. Nope. So this is proof that these two are somehow different, okay? How do we know they're different? Well, they're mirror images of one another. It's as if we put a mirror in between these two guys. This actually works out kind of nice. It looks like this guy's getting ready for school in the mornings. Oh, you look good. And this guy on the other side is, no, you look terrible, and whatever. But they're mirror images of one another. The green matches up with this one. The red is kind of a mirror image of that guy there, and then we've got the silvers matching up here. Okay, and obviously the blues are matching up there. So yes, these do have the same chemical formula, but they are put together differently. You wouldn't think they're put together differently, but they are. Okay. Now, something as subtle as that can have drastic effects in the body, and we're going to talk about a drastic effect that you would see because of that particular example. Okay. So, enantiomers, although subtle, do have different effects. We're going to go through a couple of actual real-life cases or examples that show the different effects of these different isomers in the body, to show that, yeah, even though they've got the same chemical formula, they've got a different structural formula or some kind of spatial arrangement of the atoms, and that very slight difference, what we perceive to be as very slight with our small brains, actually plays a very, very large role in our bodies. That difference does. Okay. So the first example I took right out of the book here is a molecule called L-DOPA versus D-DOPA. Okay. So these two molecules are very similar. Okay, you can look at them and say, yeah, those look pretty much alike. They are enantiomers. They're stereoisomers of one another. If you took a mirror and put it right in the middle, they would be mirror images, right? Okay, so imagine there's a mirror right there. They're mirror images of one another. Now, the book outlines the fact that L-DOPA, they call that L-DOPA, the L stands for like left-handed dopamine or whatever. And so it's kind of got this left-handed swing to it, but don't worry about that. That's what the L stands for. It basically denotes that it's a different form, okay? Is used as an effective drug against Parkinson's disease, okay? So it probably calms some of the symptoms from Parkinson's, okay? D-DOPA, on the other side of the screen, on the right side of the screen there, is biologically inactive. Okay, so let's say you got an idiot for a doctor and you've got Parkinson's disease, and he's like, I'm just going to give you some of this DOPA stuff. It's going to be good. And he gives you the wrong kind. Okay, he gives you D-DOPA, and not knowing, it doesn't do anything in your body. And you go back to him and say, you're an idiot. I want my money back. Give me the little L-DOPA stuff. And then finally he says, oh yeah, I just learned that the other day in one of my seminars. And L-DOPA turns out to calm your Parkinson's symptoms. Okay. So whatever it is, whatever the sensitivity is, maybe it's a receptor on a cell, and we're talking about cell communication and the interaction of some of these molecules. Maybe it's a receptor on one of the cells that's shaped in a very specific way that will only accept L-DOPA, whereas those same receptors, the D-DOPA just doesn't fit in there, okay? Because no matter how you twist it or turn it, it's not the same as L-DOPA. Now, who knows why, okay? That's one of those things. The one example that is relatively famous for the human effects of stereoisomers is the drug thalidomide. Okay, thalidomide poisoning, if you want to call it that, or thalidomide disease, if you want to call it that, or sickness syndrome, is something that affected people back in the 50s, 60s, so in that era of our history, and it is a drug, or was a drug, with a mixture of enantiomers. Okay, one of the enantiomers thalidomide was given to people to reduce morning sickness. Okay, and it worked. People got thalidomide, and their morning sickness when being pregnant went away. It's like, oh my gosh, this miracle drug. What people didn't understand is that this drug, with a mixture of the other enantiomer, was bad. Okay, so it had one of the enantiomers that created the situation where morning sickness would go away, and yet it had its other enantiomer that caused severe birth defects. Okay, and so it's a subtle, it's a mirror image of the good one created bad things, really, really bad things. And so mothers who took this had sons and daughters that looked like the pictures that you see in front of you. They came out with, the children came out with severely malformed extremities. And so apparently I've done a little study on what it does, but somehow, some way, the oddly shaped one, the one that causes the birth defects, somehow interacts with your genome or the cell during a certain stage of development, and that stage of development happened to be when the arms and the extremities and the legs and feet and things like that were forming. Okay, and so you get kids who have sometimes got no hands. They've got little like almost looks like flippers, for a lack of a better term, for hands, and it was terrible, right? Now they saw this and they're like, okay, we understand what's going on. That it was a tragedy what happened. We're going to try and create this situation where we're going to still use thalidomide, but we're only going to use the one that's good. And so they purified this drug. They said, okay, if we get rid of the bad ones, now we know there's bad isomers in there. We get rid of those. We purify the good stuff. We give it to the people, and everything will be fine. And it turns out they did all those steps. They gave the good thalidomide to people. Their morning sickness went away. Oh my gosh, they're still having children with these birth defects. And it turns out that even in this purified good form, the good one can spontaneously convert to the mirror image. Don't ask me how that happens. I have no idea. Ask somebody who's way more smart than I am, and you'll probably get an answer, or you can do some research yourself. But they spontaneously switched from this good form, okay, this one version which cured morning sickness, to a bad version while it was in the mother's body and the fetus's body, and then still cause those birth defects on top of it. Now, you saw a lot of this in Europe, in European countries, and the reason for that is because the reason you didn't see a whole lot of this going on in America is because of the FDA. Okay, so when you hear about Russia, doing some kind of coronavirus vaccine and trying to get it out to people like now, and it hasn't been much testing behind it, you should have a respect for the FDA, okay? At least in this respect, right? They saved an entire generation from countless tragedies, okay? And they oftentimes get a bad rap, but the FDA does do these types of things, and they have these testing procedures for a reason, okay? So, thalidomide is a great example of how very small, subtle changes in the structure, the isometric structure of one form versus another can have drastic effects on the human body. The last example I'd like to give here of isomers and how they're used or seen, I got to put my glasses on for this one, how they're used or seen in the human body is an example known as rhodopsin, okay? And this one is found in the rods of our eyes. And if you know what the rods do, say it out loud to yourself right now. If you know what the cones do, say it out loud to yourself. The rods in your eyes will sense light, and the cones will sense color. Okay? And so within this rod, there are these little discs, and these discs are responsible basically for sensing the light. Okay? And these discs are made up of these proteins called rhodopsin. Okay? It's a combination of two different proteins called retinal and opsin. All right, so this big kind of like, it looks like almost like a barbell, purple barbell, that is a protein called rhodopsin, and that is the light sensing molecule in your eyes, and it's located in the rods on these little discs. Okay, so let's look and see what the structure, and incidentally, you don't have to know the structures of these things, but let's look at the structure of rhodopsin and see what's going on. Okay, so there are two forms of rhodopsin. There is the cis isomer, okay, cis rhodopsin, and then there is the trans rhodopsin, trans isomer of rhodopsin. Now, what happens when photons of light enter your eyeballs is that they interact. Now we're looking, remember, we're talking about, when we're talking about cis and trans, we're talking about these are geometric isomers and they revolve around a double bond, right? And I believe that the double bond in question is right here, okay? That double bond right there is the one that we're looking at. And so we've got this big chunky group way out here, and we've got this big chunky group way out here, okay, right out there. And so those would be kind of like the chlorine molecules that we had I had shown you before. Okay, let me just quickly do this. Okay, remember? So there's our one chunky group I saw in that diagram. Here's the other chunky group. They're on the same side of that double bond. Okay, let me minimize. All right, so there's one of them. And here's the other one. Now when light hits this molecule, what it does is it causes a chemical change in this double bond. It causes it to break, and then I believe it causes it to break, rotate, and then reform that double bond. And so now down here, this is really hard to see, and it's hard to track, but I believe that the double bond is right here. Okay, that same double bond of interest, this one, I believe that it is right here. And so we see this on this side of the double bond, this is big chunky thing, and on the opposite side of the double bond we have this chunky thing. Okay, so what it's done is it's caused this, the light has caused this change, this shift in structure from a cis isomer to a trans isomer, because it breaks the double bond of interest, it rotates, and then it reconnects the double bond in the trans conformation. And so what this does, this subtle change from cis to trans probably creates some kind of mechanical deformation, some kind of change in shape of this protein, which then is transmitted or relayed through this rod cell to the cell body, and then ultimately produces some kind of electrical action potential, some kind of electrical signal that's sent to the brain, and it says the brain, there's light. There are photons of light that just made this thing happen. Okay, if you wanted to get a little bit better understanding of what that process is, you can read this slide. It's a slide that kind of outlines how this process happens in rhodopsin. Okay, I'm not going to go over it, but it is relatively interesting. Okay, so there you have it. Chapter 4 is complete in the books. We'll have a couple of different things we're going to do with Chapter 4, and this will be once it's put up on Google Classroom. Well, it's too late to get that message now, but you can watch it whenever the heck you want. I will see you guys at our next meeting.